Hello, today we're going to put together everything we've learned so far with hypothesis testing to do a hypothesis test. These are quite long questions, sometimes 6 or 7 marks, and there are a great number of steps to it. But actually this is a method, and this method is very similar each time. You just have to decide what to do at each of the following steps. So I'd suggest adding these steps to your notes. We're going to run through each step, roughly what to do, and then we're going to have a go at some. We're going to do one tail test first and then two tail tests. Ultimately, they're very similar. It's just a slightly different change at step 3. So step 1, we need to decide on a test statistic. In year 1, this will always be binomial. In year 2, there are a couple more options coming up. We need to come up with some hypotheses, our null and our alternate, which we've done for the past lesson or two. We need to work out if this is a one-tail or two-tail, so this will be best depending on our alternate hypothesis. So a two-tail test will leave open two options that we have to check. For step 4, we need to work out either critical regions or decide if we are in the critical region. We're going to look a bit more about that this lesson. Step 5 is a comparison to the significance. So we say, is this significant? Is it not significant? Do we accept H0? Do we reject H0? And then for step 6, we need a conclusion in context, if there is any context given in the question. Because mostly these are about dice or tests or medical surveys. So let's have a look and see if we can get through these steps. So add these to your notes and I'll try and point out which step we're doing at each bit. So here we have a question about Bob and his dice. He's been told that dice is fair, so probability 1 out of 6 for getting a 6. He rolls it 20 times and only gets 1 6. Decided whether or not it's biased against landing on a 6. So step 1, we need a test statistic. So here is my test statistic. We're going to be using binomial with 20 attempts with a probability p. Our H0 is going to be p equals 1 out of 6. So this is fair. And our H1, our alternative, is going to be probability is less than 1 out of 6. So this is for biased against a 6. So we're not entertaining the possibility that it might be greater than a 6, a bias towards a 6, because in the question we're told specifically to see if it is biased against landing on a 6. So we're going to assume it's fair, but if the probabilities of getting this result with it being fair is really small, we might accept this instead, that it's biased against a 6. So this is step 1 and step 2, and they kind of go together to set things up. So step 3, if we flick backwards, is to work out if this is a one-tail or two-tail and work out our significance. So this is a one-tail because there's only one option here. %10 test. So this is step 3. Step 3 is really just deciding exactly how we're going to calculate this. Step 4 is to work out the critical regions or see if we're in the critical region. So now we're on the right page. We kind of find the critical regions. So let's try doing the critical region. So we want to find the probability that x is less than or equal to some number is less than 10%. Because it's a 10% test, because it's only one tail, we don't have to half anything. So if I grab my calculator, so I'm on menu, distribution mode, binomial CD. We're doing binomial CD because there's a less than or equal to in here. Variable, so we've got n is 20. My probability in here is my 1 over 6. 1 over 6. Let's try 2. So two or less 6s, 2 or fewer 6s, that's like 32%. Let's try 1. That's like 13%. Let's try no 6s. That's 2.6%. So let's make a note of these so we can find our critical region. So probability x is less than or equal to 0 is 0.026, and probability x is less than or equal to 1 is, we also need our 1, so go back here, go put a 1 in here. We get 13%, so 0.130. So our critical region, using last lesson, is x is less than or equal to 1. So, no, our critical region isn't 1, our critical region is 0, because we're after less than 10% and this 13% here is bigger. So our critical region is actually less than or equal to 0. So if we got no successes, it would be so unlikely that this dice is fair, we would expect actually it's biased against sixes. So this is finding the critical region. We could also just see in here there's one success, and our one success here is bigger than our critical region. So we didn't need to find this, we could just look at this one here and go x equals 1, not in critical region, as probability x is less than or equal to 1 is greater than 10%. So here you have our two different ways of looking at this. Way 1 was to find the critical region and go 1 not in critical region. X equals 1 is not in the critical region. Or we looked at x equals 1 and did less than or equal to 1 and it was not in the critical region because it's bigger than 10%. So either way we've decided here this is not unlikely enough. The chance of this or worse happening is bigger than 10%. So both of these two things, or either of these two, you only need to do one. Either do a critical region and go 1 is not a critical region thing, or we tested x is 1, should be less than or equal to 1. But x is 1 is not in our critical region, because this probability here comes out to be bigger than 10%. And if something has a chance of 10% or more of happening, we're going to say we believe it. If the chance is less than 10%, don't believe it. But this chance here is bigger than 10%. I know it's weird that we have this less than or equal to, but we're not after is the probability bigger than 10%, we're after is this in the 10% of least likely outcomes. So either way, there is evidence to accept H0. So this here is our step 5. Let's go back to this. This is our step 5. So we're comparing to the significance. There is evidence to accept H0 as probability x is less than or equal to 1 is greater than 10%. Greater than 10%. So because this probability is bigger than 10%, it's not significant. Some people actually write not significant in here. So because this probability is bigger than 10%, we're going to accept H0. So our conclusion is going to be that this suggests die is fair. Now you might look at this and think, no, this probability is actually quite low. It's only 13%, but 10% was our threshold for saying no, we don't believe that happens. It's got to be less than 10%. So even though this was 13%, it's still unlikely. It's not unlikely enough for our test to say we don't believe this could happen with a fair dice. So 10% here is our threshold. So this here would be step 6 at the bottom, which is a conclusion in context for our problem. So the hypothesis test in this case, with these results in this setup, suggests that this could be a fair dice. It's not unlikely enough for us to say that we don't believe this dice is fair. For our second example, we have a medical treatment. Assume it's medical treatment, yeah, medical treatment for a disease. A certain doctor is undertaking some research and has produced a new drug which is successful at 11 out of 20 patients. Now if this is 2/5, this would suggest only 8 out of 20 would be successful. So clearly this has improved a little bit. Doctor claims that the new drug represents an improvement. So again, because there are 20 things, we're going to be using x is a binomial. 20, comma p. H0 is p equals, we're going to use our 2/5 from here as if nothing had changed. And our H1 is p is greater than 2/5, and this is improve. So if there is enough evidence to say this isn't true, our assumption is going to be it's improved. So this is a one-tail 5% test. So we want to be 95% sure with only a 5% margin for inaccurate testing. So if the chance of it happening is less than 5%, or that or worse happening is less than 5%, we're going to reject H0. So basically we're trying to work out how unlikely is 11 or better treatments and see if this is less than 5%. So we've got our step 1, which is our test statistic, and our step 2, which is our hypotheses, and our step 3, which is our tails. We either now need to work out the critical region, or we need to do a probability test. The probability test is what we're going to start off with. So we're going to look at the probability that x is greater than or equal to 11. Why 11? Because in here we had 11 successes, and this is probability is greater than, so we need to test 11 or higher. This is 1 minus probability x is less than or equal to 10. Because if you remember 9, 10, 11, to do 11 or higher, we need to take off everything up to and including 10. So this is, I'm going to reach for my calculator, because we've got a less than or equal to, we're on binomial CD. So we've got 10 in here, 20, we need to put our probability change in here. This is 2 out of 5. Press equals, so we get 1 minus 0.8725, which is 0.1275. So we need to look at this and decide, is this bigger than 5%, yes or no? So our next step, we could also find the critical region. If instead of doing this probability test to see if it is bigger than 5%, we could look at what probability is 5%. So you could test 12, 13, find the point where you get 5%. It's probably going to be 12 or 13. So you could find the critical region just like we did last time. So our comparison to the significance is as probability x is greater than or equal to 11 equals 0.1275, which is greater than 5%, evident to accept H0. So because this probability is bigger than 5%, we're going to stick to H0, which is probably there's been no change. Because this probability is bigger than our 5% threshold for saying nope, don't believe that happened. So this suggests no change in success. Let's put this way you can see it. So even though this looks like an improvement, it's not significant enough for us to say it definitely represents a change. If you want to try and make this work, we're going to need a bigger sample in order to narrow down the probabilities. And a lot more of this is covered in year 2. So on the virtue of this test, it suggests that the improvement isn't big enough to warrant it being a definite improvement. It might just be down to luck. So we have a 5% threshold here, and this still has a 12.75 chance of happening. Okay, one-tail tests. We need to have a go at some here from 7C. These are all one-tail tests, so they're always greater than or less than. In general, the less than tests are so much easier because you don't have to do this 1 minus bit. If you remember back to the first test we just did probability x is less than 1, x is less than 2, and had a look to see if we can see if it's less than the significance. So less than tests are always easier than greater than tests. Okay, the other part of this exercise asks us to do two-tail tests. So we're going to have a go at this. It's exactly the same, except when we come to do tails, we're going to have to look at two different tails to see which one we think might be correct. So we've got 10 people here, so we're going to be using x as a binomial 10, p. So we've got our binomial. This is for the ratio of non-vegetarian to vegetarian meals, and we normally expect it to be 2 to 1. So our H0 is probability of vegetarian, is P, is 1/3. So ratio of 2 to 1, this would give us a 1/3 probability. Manuel's restaurant uses around 10 people and one person ordered a vegetarian meal. Test whether or not it's different. So our H1 is going to be P is not equal to 1/3. So this is different. So this leaves open two options. It could be greater than 1/3 or less than 1/3. So this is a two-tail, 5%. So this is actually 2 times 2.5% for our tails. Because we've got two tails, it's a total 5%, so we need two lots of 2.5%. So basically what we're trying to do is work out, is probability x is less than or equal to 1 less than 2.5% for the lower tail, and is probability x is greater than or equal to 1 less than 2.5%. So these, if you think about it, are our two tails. This is basically like doing both of the one-tail tests, but with half the significance for each of them. So with this, I'm going to use a binomial. We need to change this n value to 10. Our probability is 1 out of 3, 1/3. And we're going to start off with 1 on binomial CD. So this one, probability x is less than or equal to 1, is 0.104. So this is not significant. Because this tail is quite small, the other tail is automatically going to be quite big. So if we had a look at this one, this would be 1 minus probability x is less than or equal to 0. Because if you don't remember, we've got 0, 1, 2, we want 1 or greater, we just need to take away 0. So if I put 0 in here in my calculator, we get 1 minus 0.01734, which gives us 0.98266. Clearly this is bigger than 2.5%, so this one is. Not significant either. Neither of these are smaller than our 2.5%. So either of these two outcomes, bigger than 1/3 or less than 1/3, could have happened with a probability bigger than 2.5%. So yeah, 2.5%. So this means we have evidence to accept H0 and conclude proportion has not changed. They've gone with ratio. Ratio has not changed from 2 to 1. So what we need for this test to be the other way round is we need one of these two things to be less than our significance, one of these two things to be very unlikely, less than 2.5%, and then we would say evidence to reject H0 and conclude that the ratio has changed. But either of these two things are believable when our threshold for believing is 2.5%. You might find when you come to look at some people's solutions that they don't test this other tail. Because if we were doing 10 things with a probability of a third, we would expect 3 and a bit successes. So clearly, one or more is going to include things like 3. 3 would be the next one on here. And 3 is very, very likely, because 3 is what we would expect to get. Because 10 things, 1/3 chance of success. So you might find some people write down a statement, rather than doing a probability test, they say, obviously x is greater than or equal to, probability x is greater than or equal to 1 is bigger than 2.5%. Let's put some question marks in here, because that's what we're testing. So some people won't test the more obvious tail. Sometimes they make an argument like, clearly it's bigger, but when I'm doing hypothesis tests, it's usually easier just to test the other tail and see. So you could have done this by finding critical regions, or you can do it just by looking at probabilities and seeing if they're in the critical region or not. Reminder that we do not equal to 1, but greater than 1 or less than, greater than or equal to 1, less than or equal to 1, because we're looking for tails, so all the way from that outcome to include all the outcomes more extreme than it. Okay, on this slide here is a hypothesis test template. If you were ever trying to work out how a hypothesis test works, it's every time this exact same couple of steps. We've got our hypotheses. I like to write down what my hypotheses mean, because p equals a third. When you come to do your conclusion, you then have to look back and work out what was p and what does that mean for the context and what does this mean for the restaurant. So I quite like to write in here what these things mean. So if you look in here, I wrote down my hypothesis here, and I wrote down different in here just as a reminder for what this meant. My significance, and then we need to decide how many tails this is, what our test statistic is. You can then either do your lower critical region or your upper critical region. If you're not in the critical region, we accept H0. If we're in the critical region, we reject H0, and then our conclusion at the end. Have a go at this exercise 7D. This is actually the end of year 1 stats, which is nice, but hypothesis tests will take a long time to get through, and a long time before you feel proficient in it. Out of all the topics from year 1 stats that we ask for revision sessions in year 2, it's always hypothesis tests and binomial, because it will take quite a while to get used to it, and it might only be when we start doing the year 2 stuff that you fully understand how hypothesis tests work. So persevere with it, but remember we're around to help you if you get stuck.